Welcome back to this progressive live lab. Hi, Tamal.
Hello, glad to be back.
Hi. So after this previous iteration of the lab, we are at a state where we have the two Kubernetes clusters, M1 and M2. We have the kube vault running with the secret. And on M2, we have the secrets operator from HashiCorp, which is retrieving the secrets. Both clusters are set up with all the basic infrastructure needs, ingress controllers, load balancers, CSI drivers, dashboards from Kubernetes, and also Grafana and Prometheus. Now, we've also seen that we have retrieved the secrets. They are available in the SockShop namespace as 5 secrets for the 5 databases. Another interesting, in the previous video, we had a very good conversation with Tamal, understanding how KubeDB as an operator works, and we have deployed the KubeDB operator. Now that's the state we are in. It's all set to deploy SockShop as an application set. Now for some of you or many of you who have worked with SockShop, it's pretty straight and simple, right? I mean, if I look at it, this is how it looks like. Yeah, it's a nice use case for a polyglot architecture to be showcasing Kubernetes capabilities. In its most basic form, if I go to the creators of SockShop, it's not something that I have created, so all the credit goes to Weaveworks, who's the original creator of SockShop microservices GitHub, let's say that, right? And it's used popularly by many teams, to showcase Kubernetes. But the thing about this particular version, the original version, is that if I look at the deployments, so it gives you a lot of good options to deploy on Docker Compose or Kubernetes. And in Kubernetes, you can look at complete demo.yaml. This is the first starting point. And this is where you will get a non-persistent with single replica using simple image of MySQL, Mongo, or whatever. And then it's a completely 800 line deployment, but it's a demo. And this is where, we move away from a demo to a production grade environment, simulating SockShop. In that case, you have to bring in, the first thing is a state of persistence to these databases, which in my medium.com article around SockShop, we had demonstrated the use of PowerStore, one of the important portfolio of Dell as a storage array. And we had, if you look here, demonstrated SockShop as a reference architecture for various use cases, where we had used PowerStore as the persistence layer. Again, single replica, no HA in SockShop microservices or databases, but bringing the level of persistence that it requires for a database to operate. And then we went on to integrate EKS Anywhere with SockShop with persistence layer with Dell's PowerProtect Data Manager, which is all about taking an entire state of a Kubernetes cluster and its namespaces and backing it up either locally or in the cloud, and then restoring it back in case of a disaster. And we have in this blog very interesting video conversation like the one that we are having here, deploying a SockShop application with PowerStore, this single persistence layer, and then deleting the entire namespace of SockShop and resurrecting the entire namespace to the state where we had created some entries in the database as orders and things like that. The entire namespace was recovered to a point in time that we desired. Now, while that was a gradual build-up, we showed persistence, we showed data protection. We then also moved ahead with how do we use Power Protect Data Manager not only as a backup and recovery, but that's not from a database standpoint. It mainly works at a namespace and a Kubernetes construct standpoint, but also then being able to take this advantage of having a disaster or a backup copy of the namespace and porting it across a cloud provider, which in the case of this particular blog, we had demonstrated how you can take up workload from EKS running in the public cloud. So we had deployed SockShop in EKS in the public cloud, taken a backup copy of that on Power Protect Data Manager, and recovered that state onto a local EKS Anywhere cluster. And while we did it from EKS to EKS Anywhere, there is no reason we could not do it on EKS to an OpenShift or a Rancher or whatever mix that you can think of, or from an EKS to an AKS environment. Now, this is where we are still working to explore the capabilities with the very basic template. Our database construct, the main heart behind the whole data plane, was still single replicas. And we were not really working with how databases in the enterprises typically are, right? And this is where this particular blog, or what we are doing with this live lab, steers away from that simple use case into bringing in the level of complexity that is required to demonstrate for a polyglot application, which is where we are now talking about many different things, including the persistence layer, including secrets management, including running these persistent workloads in a HA mode with a operator framework, and then bringing in all the nuances of shebang of different things actually into the mix. Now, I would love to explore this scenario even further as we move on, and we will build upon this lab by introducing analytics and things like that. That's a future roadmap. But for now, let's now continue as to what we will be doing. Now, at a state where we have deployed KubeDB operator, we will be deploying the SockShop application itself. Now, SockShop application has been, the wiring has been done differently. The manifests are different than the original one, mainly to actually accommodate the database layer through the CRDs of KubeDB. Okay, and I will show that to you in a bit. The manifests are stored on the GitHub repo in a zip file format. So we will download this. Interestingly, as of today, RabbitMQ operator is not a feature in KubeDB's portfolio, but I'm hoping this will also come up in the near-term release. So for now, we will separately install the RabbitMQ operator to run our RabbitMQ instance, which is the queue processor used for loose coupling, building a RabbitMQ queue for various transactions. So this is the RabbitMQ operator. For all the other things, it will be KubeDB, which is the manifests are there inside of this zip itself. We will unzip, and then the namespace for SockShop is already created. So there's a YAML reference inside the customization file. So I will remove that namespace creation. Plus the creds, the database credentials were stored as a static YAML in the zip file, which is we were building the secrets to a YAML definition, like how you create a Kubernetes secret. We are removing the reference of that from the customization because we are no longer using these statically defined secrets. We will be consuming the secrets which have been given to us by the secrets operator from Vault. And then we go on to deploy the entire thing. Now let's start, and I will move to this point. Let me copy this. And let me make sure I am on the client cluster, which is the the bigger cluster M2. Okay. And like I said, it's a live lab. If something would have changed overnight, while I was dreaming of something and I would have changed something, I don't know, we will simply troubleshoot a little and get back the state to how it should be. For now, I'll just go ahead and do this. Okay, so the zip file has been decompressed. You can see that there are these files which are actually located inside of that folder, and I'll talk to you about all these. Interestingly, this static creds, DB creds, is I'm removing the reference to deploy this to the customization. And I am also, there were two things that we did, right? One is and the namespace. So namespace is already created. Now, let's look at the customization itself file. More and go incrementally on that. So you can see that I have locust, which will be my load testing YAML. This is an important part where I think again KubeDB shines out, is that when I create a database, there are requirements sometimes of initializing the database with a seeded value set. It could be due to a migration or A, B, C, whatever it is. So we are in KubeDB, the initialization of a data set inside a database can be supported through config maps, and it's pretty standard. It's well documented on the KubeDB site of how to do it. These 4 init config maps, these are actually config maps which have the data set inside of them, and then we just load these config maps when the database creation happens. These are the services that will be, the data services. So we are creating user, catalog, orders and all this, and with the prefix of the type of the database here. These are the microservices that will be created as a part of the deployment. The front end, the HPA for that front end, and all the other services, the ingress definition, and there are some patches that I wanted to talk about, which is basically to make sure that, like we said, we have a node pool structure. So the node pool structure would allow us to put, the microservices into the group called as MD1. Okay, so the cards is a microservice, so all that will come on MD1. So all the microservices will come up on MD1. Okay, now for the stateful applications, they are defined as a part of the CRD. So now let's look at the CRD, which will create or instantiate a object for a MySQL database or a MongoDB or a Redis. So if I look at the files here, let's look at one of the files, which is for MySQL. This is the catalog database for the SockShop application. And you can see how easy it is to create a database on Kubernetes in a proper, enterprise grade format here. So this is the name of the CRD that is used by KubeDB to detect that a request has come in to create a database object. The name, the namespace, the version. On the website of KubeDB, you could easily see the versions that are supported, and I think there is plenty of support for old versions and newer versions, so there's a good range of support there. What's also important is this field called as auth secret, and this is where the reference to an externally managed database secret. If you don't want to and you want to spin up a database and let KubeDB generate the database credentials, you just have to exclude this particular statement and it will supply, a database secret for you. Else you can reference your own database secret here. Now, this is what we are retrieving. This is one of the 5 secrets that was retrieved from the secrets operator. Then the topology could be a single replica or a group replication mode. So we are saying 3 replicas. The storage class name, sorry about this power store, I can change it whatever, but I have not specified any storage class. So the storage class will be the default storage class, which is actually about PowerFlex storage class. So we will see that once the MySQL database comes up, we will have 3 persistent volumes for this database running on PowerFlex software-defined storage from there. Again, the init, this is the part where I specify the initialization of the database with a dataset. And lastly, like I said, we will make sure that these pods come up on the MD0 pool. So the node selector allows me to do that. So far, so good for the MySQL database. Likewise, let's see one of the MongoDB CRD definition. Like a MySQL, I think I like, Kamal, the way you have kept it simple by the name of the database provider. It's easy.
Yeah, I mean, we made it so that it's uniform across all these different database types for pretty much all the common sort of attributes or features of a database, right? I mean, it's the just the replicas, and this is MongoDB, so here we have to also specify sort of a replica set name. But other than that, is the MySQL and the MongoDB YAML file looks pretty much the same.
Yeah. So again, range of support for the versions pretty much covered, from running different versions. Same goes true for the auth secret. We are retrieving through secrets operator, externally managed through, so that so that KubeDB does not generate the secrets for you. Storage class name default, same thing. And again, I'm seeding the database with some entries, so a config map that will support that. And then finally the node selector here. So, and we have 3 MongoDB databases. I'm not going to go through all of them. So we just saw cards. The other 2 are orders and user. The other one is the Redis, which is used for session DB, just to manage, because our front end is going to be horizontally scaled. Obviously, the state in terms of the session has to be persisted outside of the front end, and which is where we bring Redis as the supporting engine to manage that state of our logged in session. So the cookies and everything will be persisted in the Redis. So now in order to do that, we have to have a Redis DB, which is now again through KubeDB. So if I say cat Redis DB session, a very similar look and feel, kind as Redis, name, auth secret, the version, storage class name will be defaulted to PowerFlex storage class, and then the group selector, the node selector, which is MD0. So far so good. Like I said, the only other missing piece is the RabbitMQ. So RabbitMQ is being managed through the RabbitMQ operator. So if I look at the RabbitMQ queue processor here, this is an instantiation of the RabbitMQ operator CRD, which is to create a RabbitMQ cluster. Again, not a single replica, but 3 replicas, some resources, okay, and some of the initial, password and things like that. So now, if you have seen this, we are all set to, okay, so the other part is the TLS. This is an ingress object. So let's look at it. So these are the certs for my wildcard cert, supporting my domain and a wildcard entry for that. So it's basically, now we could have done this also as a stored secret in Vault. Simplicity, I think point is you understand Vault and everything else. Now this was, I mean, we could have, there's another use case of Vault, right, for storing TLS secrets as well. We could have done that. For now, we just go ahead with this momentum. And then let's see kubectl get pods minus n SockShop. So as of now, we just have one pod running, which is the secrets operator. There is nothing else running. So let's just apply the customization. And create these deployments. And when this happens, you can see that all of these have been successfully created. We will see the result of that in a bit. For now, let's understand what has happened. A lot of things would have happened in the backend. So let's look at one by one. The pods which are representative of the microservices would be straight away a clean deployment, right? So you can see that all the front end, the orders, anything without the DB suffix, right, is come up actually, right? And RabbitMQ is separately coming up. I can see a catalog DB, carts DB, which is the KubeDB managed entities. They are all in their init state actually. Okay. Now let's look at, while we look at the pods, let's look at how the KubeDB will view things actually. Okay. So if I look at KubeDB get MySQL, now MySQL is the name of the custom resource that is specified in the CRD specifications of KubeDB, and it monitors the request for a resource CRD type of MySQL. kubectl gets MySQL minus n SockShop. So you can see that right now it's in a state of provisioning. Okay. And obviously what we need is basically in a running state or ready state, basically, right? So there are a lot of things that is doing in the backend. Likewise, if I look at kubectl get MongoDB, in this namespace, you can see that there are 3 databases which are in the provisioning state. And likewise, in the for Redis as the CRD. Okay, so the Redis is already done. It's already in a ready state. The other 2 are in the provisioning state. It will take about a minute or so to get things converged to a ready state. For now, we will just pause this video and resume when it's done. Okay, so by now, given the state of affairs, we should be able to see a ready state of the MySQL database. Let's validate that. Sorry, the namespace has a hyphen. So one can see that the MySQL database, and it's a very simple expression, kubectl get MySQL, and this is how I would love to see it, right? Give me all the names of MySQL databases. Catalog DB in a state of ready. Okay. Let's also look at kubectl get MongoDB in the SockShop namespace. So there are 3 databases, cards DB, orders DB, and user DB, all 3 in the ready state. Redis, we had already seen that it was in the ready state. The ready state implies much more than the pod actually being available. Okay, and this is the difference that I want to talk about from a stateful and application-oriented aware CRD, as opposed to just deploying a MySQL pod or a, where the state of the pod may be ready, but there is something else happening which we are not sure of, and some errors. So this ready state is good for us to go ahead. We will also look at the pods in the SockShop namespace, and you can see that all the pods are running for the databases, and the microservices are also running. Now, interestingly, what I observed through my own practical experience as we were working through wiring this up is that KubeDB operator will remain in provisioning state which means even the pods will not be seen if it doesn't feel something is wrong, or if it feels something is wrong, which means that I have the ability to troubleshoot only on one end with monitoring the logs of the KubeDB operator, which we can, if I say kubectl get pod -n KubeDB, which is the operator namespace, and see through the logs of the operator itself from the provisioner standpoint. This is, like we said, this at the heart of the, and you can see that there's a lot that's happening in this space. So let's say if there was some problem, you don't have to kind of juggle through going through pod logs and so many pods. You can work with the operator logs to understand what is happening, what's missing, and things like that. I mean, just to make sure that, because things can get haywire in Kubernetes sometimes, and you need the ability to actually have a simple way of comprehending the situation in a way that you can troubleshoot and fix it, instead of just going around and spinning around the wheel.
Yeah, one other thing I would add is when you are running these databases, another important place to check will be describe the database object itself. So that object will have this events basically, and that events will also tell you if there's any issue in terms of the provisioning process, right? Like this command, if you run this, so that the bottom section of the screen, right? These events that you see, you something is not right, you probably should also see some message there saying what it is not right.
Yeah. And recall that in this, our secret has also been mounted externally, so it's a good success from all corners. Now let's look out at the ingress part of it. Before that, let's look at the persistence. So now you can see that there is a host of persistent volumes which have been created on account of these database objects. Okay, so I can see about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 additional volumes. We started off, so 16 additional volumes should have come up on my Part5 software-defined storage from Dell. In addition to what was there, we started off with 5 volumes, which was my earlier scenarios. We created the Vault server, a replica set of 3, which made the total as 5 plus 3, 8. And did I say 17? I don't know what numbers did I say. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. I am not very good with numbers, but 16 is what I will remember. and let's go to validate this by logging into the Powerflex UI. So if I look at the volumes, I can see 24 volumes have been created, okay, which is 5 plus 3, 8, 5 original, 3 Cube Vault, and now 16. So yeah, the tally is proper. Interestingly, these are all thin provision. So that's another nice thing, especially when you are deploying Powerflex in the cloud. EBS, the native service, does not have the ability to thin provision storage, which means that you pay up for whatever you provision for, whether it's being used, not used, doesn't matter. With Powerflex running in the cloud, you really have the opportunity to optimize your costs by doing thin provisioning and then incrementing your capacities as you get closer and your whole modeling activity comes. So this is very important. While it's a norm in the on-premise side, right, of having thin provisioning in the cloud has always been a challenge. And with the advent of software-defined storage from Dell and others, but specifically the way you can combine thin provisioning with some of the other attributes in terms of compression and whatnot, you can really optimize your costs in the cloud as well. For now, let's stay on to these 24 volumes created, seen here, all good. Let's look at the ingress of how we will access this application. kubectl get ingress -n SockShop. We can see that the SockShop is advertised through the ingress IP of 59, which is mapped to the Nginx ingress controller. For simplicity, I have kept the SockShop advertised through 59 as a host entry in my local host file. Else we can do it through either external DNS or through any other entry, which means we should be able to go here and browse our application. So we get greeted by the self-signed certificate warning, which is good. Now, when you are here, I think in the previous blogs, if you have, but I'll just repeat it for brevity, and there are various things happening here. The catalog itself is coming, all this is coming from the catalog DB. So your catalog DB is working perfect. Else you would see a blank page without any catalog items. We don't have any particular user defined as of now, so I can't log in. So let me register. Let's name it as Amber. I'm going to keep it very simple, a test user that I can use just to demonstrate if the services are working. Hit register. Login is successful, which means the user DB is also successful. So catalog DB is MySQL, preceded with the catalog database entries. User DB, we've just created and validated through the login process. Then comes the cards DB, again a MongoDB. So user DB is also MongoDB object. Cards DB, which is also a MongoDB. So you can see the cards DB is working. Then I will change the shipping address. Let's just keep it simple. It's a demo, not my application. So I'm just gonna keep something just to kind of keep us afloat. So this all goes in the user profile. So obviously the user DB is working, the table is also working, payment. Okay. Whatever. So from now, you saw the catalog DB, the user DB, the cards DB. The other two are basically the other three is that there is a queue processor. There is a session DB, which is Redis, which is anyways when we do the horizontal pod scaling use case. But session DB, the orders DB and the what did I say? Session DB. I said the orders DB and the
RabbitMQ. What is the queue?
Queue processor. So when I hit proceed to checkout, obviously there'll be ordering that will be done. So it has to be persisted in the orders DB, and to loosely transact this whole thing, there is a queue processor waiting for the orders and the shipping to actually be handled. So let's proceed. So you can see that I can see a order ID has been generated. Okay. And the status is shipped. So we know that the queue processing is working, which is the RabbitMQ part of it. We also know that the MongoDB object for, let's say, if I'll go to my orders, I can see that. And I can just go ahead and order that, keep ordering that. And all of this is now, we will reference it as a baseline. Okay. And that baseline gives us a good segue into our next video, which will be around how do we do database backup and recovery. Okay, so for now, if we understand what's happened, we have all this going on, which we saw through the KubeDB construct, the Kube Vault from a secrets provider, the KubeDB from a DB provider, and we are able to engage or work with our application in the way as intended. We've just described the functionality of the services part or the various workflows, and in tandem with how the application is constructed through a arrangement of services. For now, we will take a pause on this video and we will join you in the next video with yet another interesting offering from AppsCode. Thanks, Tamal.
Thank you. See you guys in the next video. Yeah.